Assalamualaikum to one and all. This video is part 2 of the mini-series tutorial on geometric optics. This time, focusing on test items involving converging and diverging lenses. Specifically, it applies the concepts of Lensmaker's equation, image formation by lenses, and dioptic power of a lens. So just sit back, relax, watch and learn. Question number 1. When the geometric center of a lens is thicker than its edges, option letter A, it may be a converging lens. Option letter B, it has a negative focal length. Option letter C, it may be a diverging lens. And option letter D, it always forms a virtual image. Okay, so there is one or more answers. And the correct answers are option letter A, it may be a converging lens, and option letter C, it may be a diverging lens. We have the explanation in just a short while. All right, as mentioned in the question, the given lens, all right, has its geometric center thicker than its edges, as shown in this drawing. And our answer to the question is that this lens may be a converging lens and that it may also be a diverging lens. Okay, so first, the fact that its shape is that it's thicker at its geometric center than at its edges, all right, already suggests that the lens is a converging lens. All right. Now, we would like also to prove that even if the geometric center of this lens is thicker than its edges, all right, this lens may also behave as a diverging lens. Okay, how is that possible? We will make use of what we call the Lensmaker's equation. So the equation goes something like the reciprocal of the focal length, or 1 over f, is just equal to the quantity n sub 1, 2 minus 1, where n sub 1, 2 refers to the ratio, the index of refraction of the lens or of the material, all right, the material that makes up the lens. For example, the lens is made of glass. So n sub 1, 2 means the index of refraction of glass divided by the index of refraction of the surrounding medium. Usually, the surrounding medium is air, whose index of refraction is, of course, 1.00. Right? So if the surrounding medium is air, and that the index of refraction of the lens, for example, is 1.5, then the quantity n sub 1, 2 minus 1, okay, will just be 1.5 minus 1, or we get a positive number 0.5, right? But in this problem, okay, since we're going to prove that a lens such as the one shown here in the drawing can also become a diverging lens, all right? That is, if the surrounding medium is not air. For example, if the surrounding medium is a liquid whose index of refraction is higher than that of the lens, then this number inside this quantity of parentheses will become a negative number, right? So that is our task, to show that the focal length of such a lens will in fact be negative. So first, we will assume that the convex side of this lens, all right, the surface that curves outward relative to an observer on the left, okay, is what we call the convex surface, whose corresponding radius is denoted here by R1. So supposing R1 is equal to positive 15 centimeters, right? While the opposite surface, right, which relative to an observer on the right curves inward, all right? So when it curves inward, it is said to be a concave surface whose corresponding radius is denoted by R2. So supposing that R2 is equal to negative 25 centimeters. Now, the sign for each of these radii, okay, is following the convention, right? In using this Lensmaker's equation, okay, we will follow the convention that the first radius, all right, the one that is uh, convex, or the one that has a surface, convex surface, will have a positive radius, and the convex or concave surface will have a negative radius. So that's just a convention. Okay, one of the conventions in using this Lensmaker's equation. In addition, we will also assume that the index of refraction of the lens itself, that is made of glass, denoted by N1, is equal to 1.5, while the surrounding medium is not air, right? Supposing the surrounding medium is a liquid whose refractive index, denoted by N2, is higher than that of the lens, okay, like N2 equals 1.6. So, using this Lensmaker's equation and plugging in the quantities, we get 1 over F equals 0.94, right? 0.94 is obtained by dividing 1.5 by 1.6, right? So that's 0.94. And we will be subtracting 1 from 0.94. So this will actually become a negative number. Then, that will be multiplied by 1 over 15 centimeters. This is the reciprocal of R1, all right, minus the reciprocal of R2, all right. The original sign is plus, but since R2 is negative 25, so we will have minus or plus 1 over negative 25. So that becomes 1 over 15 centimeters minus 1 over 25 centimeters. When we do our math, all right, 0.94 minus 1 will in fact be equal to negative 0.36. And when multiplied to 1 over 15 centimeters minus 1 over 25 centimeters, the value of whatever comes out is actually the reciprocal of the focal length, or 1 over f. So simplifying further, right, we will actually get the value of the focal length, f equals negative 104 centimeters, right? So a negative focal length means that the lens, okay, turns out to be a diverging lens, right? What is supposed to be a lens that is thicker at its geometric center than at its edges, when immersed in a liquid whose index of refraction is higher than that of the lens, okay, would in fact become a diverging lens. So that is the explanation why one of the answers to this question is that the lens may be a diverging lens, right? Both options A and C are correct. The lens may be a converging lens if the surrounding medium is air, but it becomes a diverging lens if the surrounding medium is a liquid whose refractive index is higher than that of the lens. So once again, to reiterate, our answers for question number 1 are option A and option C. All right? Option B is not necessarily correct, because if the surrounding medium is air whose index of refraction is 1.0, then it would uh, turn out that the focal length would have been positive, right? So this is not necessarily true. Option D, either, is not necessarily true, right? Uh, it says here, when the geometric center of a lens is thicker than its edges, it always forms a virtual image, all right? So a lens with its geometric center thicker than its edges describes a converging lens. While it is true that a converging lens can also form a virtual image, all right? Uh, the case where the location of the object is such that it is less than the focal length, all right? The resulting image would be virtual, enlarged, and direct. But for all other cases, uh, the resulting image formed by a converging lens are real, inverted, or with a size that can be either bigger than the object, smaller than the object, or of the same size of the object. All right? But that is if the lens, all right, behaves as a converging lens. But as we have shown earlier, all right, when this lens, although the geometric center is thicker than its edges, when it is immersed in a liquid with a higher index of refraction compared to the index of refraction of the lens itself, all right, then it turned out that the focal length is negative, all right, implying that the lens behaves as what we call diverging lens, right? Question number 2. A lens is to be used to focus sunlight on a piece of paper to ignite it. If the focal length of the lens is 80 millimeters, how far should it be held from the paper, and what kind of lens is to be used? Option letter A, less than 80 millimeters, and the lens must be converging lens. Option letter B, equal to 80 millimeters, and the type of lens is converging. Option letter C, equal to 160 millimeters, and the lens must be diverging. And option letter D, greater than 160 millimeters, and the type of lens is diverging. The correct answer is option letter B, right? Um, the uh, the lens must be held, all right, equal to 80 millimeters, right, which is exactly the same as the focal length. In other words, this means that uh, the lens itself should be placed exactly at the focus of a converging lens. Okay, so more explanations in just a short while. Only a converging lens can focus the rays of a distant object such as the sun, right? Whose incident rays are considered parallel to the principal axis. So when refracted, the rays converge towards the focal point, right? Something that a diverging lens cannot do, right? The lens, such as a magnifying glass, um, must be held from the paper a distance equal to 80 millimeters, or exactly equal to the focal length, right? That means this lens must be placed exactly at the focus of this converging lens so that the rays of the sun will be converged exactly at the focus, and there is a probability that this kind of what you call technique, you know, can produce uh, fire, right? The paper might ignite because of the concentrated rays of the sun, exactly where the paper is located. Okay, the energy of the sun is concentrated exactly at the focus, so the paper can easily be ignited. Question number 3. An object is placed 50 centimeters from a diverging lens of focal length negative 25 centimeters. The image produced will be option letter A, inverted and the same size as the object. Option letter B, the image produced will be erect and virtual. Option letter C, the image produced will be inverted and reduced. And option letter D, the image produced will be erect and enlarged. The correct answer is option letter B. The image produced will be erect and virtual. We have the explanation in just a while. We can compute the image distance di using this derived formula. Di equals the product of do times the focal length divided by the difference between the object distance and the focal length, or quantity do minus f. So plugging in the quantities into this formula, we have di equals 50 centimeters. That's the value of do multiplied by negative 25 centimeters, which is the focal length. Then divide this whole thing by 50 centimeters minus negative 25 centimeters. So when we do our math, we get the value for the image distance equals negative 16.7 centimeters. All right? And a negative image distance means that it is virtual, the image is virtual and erect, right? We say that a diverging lens always forms an erect image. So that is the explanations why our answer to question number 3 is option letter B. Question number 4. In a scene from a movie, a nearsighted character removes his eyeglasses and uses them to focus the nearly parallel rays of the sun to start a fire. What is physically wrong with this scene? Option A. The eyeglasses have diverging lenses and cannot be used to focus parallel rays. Option B. The eyeglasses have converging lenses and cannot be used to focus parallel rays. Option C. A fire can only be started if the image is virtual. And option D. Parallel rays cannot be focused. The correct answer is option letter A. The eyeglasses have diverging lenses and cannot be used to focus parallel rays. We have the explanation in just a short while. Early on, we already said only a converging lens can focus the sun's rays towards the focus. A diverging lens cannot do that. Let us expound more on why a nearsighted or a myopic eye should use a diverging lens, all right, as a correcting lens. So, in a myopic eye, we say that the eyeball is relatively long, all right, or that the cornea is too sharply curved. So this causes the rays from a distant object to be focused in front of the retina, right? Instead of exactly on the retina. It is focused in front of the retina. So that's why the image is not sharp. right? A person who is myopic or has a myopic eye is said to be nearsighted. All right. These are people who cannot see distant objects. Right. Right. So, in just a short while, we will explain how this vision defect can be corrected. Okay, so um, for a myopic eye, right, or a nearsighted eye, the problem is it cannot see clearly the image of an object, a distant object, all right, beyond a point known as the par point, right? So this par point, um, it is an imaginary point in front of the eye, beyond which objects appear to be blurred, right? That's why only objects that are closer to the eye or less than that distance known as the par point. It is because um, the rays of these distant objects, right, when refracted by the human eye, okay, they are focused in front of the retina instead of exactly on the retina. So that explains why a myopic eye can only see blurred images of such distant objects. All right, because of the shape of the eyeball, it is relatively too long, or that the cornea is sharply curved. All right, so this vision defect can actually be corrected simply by wearing what we call a diverging lens. Right, the diverging lens creates an image of the distant object exactly at the par point. And for a typical nearsighted eye, that's approximately 25.0 centimeters in front of the eye, right? As shown in this drawing, if this point here is the par point, all right, the uh, the role of the diverging lens is actually to create a virtual image of a distant object, all right? Remember, a diverging lens only produces, all right, a virtual erect image. So what it does is it forms the image of distant object or a distant object exactly at the par point. All right. And what happened is this virtual image formed at the par point, when refracted by the eye lens itself, okay, the eye lens will be able to focus the the real image, all right, exactly at the or on the retina. So if the image that is focused by the eye lens is exactly on the retina, that means the eye, with the help of the diverging lens, will now be able to see a sharp and clear image of a distant object. right? So that's exactly what a diverging lens does in correcting this kind of vision defect known as nearsightedness or myopia. Of course, for objects that are closer to the eye, located distance less than the far point, okay, there is no problem because they can be seen clearly or sharply by a myopic eye. The problem is only for objects that are beyond beyond the far point, right? We're down to our last question, number 5. Two diverging lenses are similar, except that lens B is rated at 20 diopters, whereas lens A is rated at 10 diopters. Compared to the focal length of lens A, the focal length of lens B is option A, 1/4 as large, option B, 1/2 as large, option C, twice larger, and option D, 4 times larger. The correct answer is option B, 1/2 as large. Our explanation is just in a short while. So when you talk about diopters, we're actually referring to the power of the lens, denoted by capital D, also known as the dioptic power, and it is equal to the reciprocal of the focal length of the lens when the focal length is expressed in meters. So, for lens A, we find the focal length FA equals 1 over the dioptic power of lens A, which is 10. So 1 over 10 is of course 0.1 meter. That is the focal length of lens A. While for lens B, its focal length FB is also the reciprocal of its dioptic power, dB, or 1 over 20. That gives us 0.05 meters as the focal length of lens B. So obviously, okay, the focal length of lens B is only 1/2 as large as the focal length of lens A. And that concludes my tutorial for this topic. Till the next episode, mabuhay, mashallah. Thank you very much for watching. Please follow me in my FB page and please don't forget